properties of acids and bases in solutions. So now next we are going to talk about what we can know about the strengths of these once they're dissolved. So there are a couple factors that we need to take into account. So let's think of just a general acid, an anion bonded to a single H. Now, for this substance to be an acid, this bond has to be polar with the partial positive on the H and the partial negative on the X. If it's the other way around, if X is a metal and it takes the partial positive charge, then the substance is going to be a base. So we need a polar bond, and specifically polar in a way that the hydrogen takes the partial positive charge. We also need a bond that's weak enough to be broken, right? The whole idea of an acid is that it's going to give up this hydrogen. So it has to have a weak enough bond that it will actually dissolve in our solution and actually break. If the bond's too strong, then the bond stays put, the substance stays bonded, it doesn't actually dissolve in our solution, it doesn't donate any H's, and so it has no effect. Additionally, the conjugate base must also be stable. So the anion on its own must be stable. So these are our three factors: the polarity of the bond strength, and the stability of the conjugate base. For binary acids, acids in which there are only two elements, the bond strength is the most important factor. So the bigger that the X atom is, the weaker the strength of the bond, and so the more acidic the acid. Remember, if the metal anion is bigger, it's more spread out, it has a weaker effective nuclear charge at its boundary, and so it's not going to be able to form as strong of a bond as a small atom would. It was very condensed and packed in. So for example, hydrogen fluoride is a weak acid, hydrofluoric acid, because the bond energy is very high. Even though these are very polar, very electronegative, it's a very strong bond, and so it doesn't completely dissociate in water, meaning it's a weak acid. Hydrochloric acid, on the other hand, is more acidic because it's got a weaker bond strength, and so it does completely dissociate in water, making it stronger. So in general, we can see our acid strength increase down a group. So down a column on the periodic table, we'll have stronger and stronger acids as our atoms get bigger and bigger and the bonds get weaker. Acid strength will also increase across a period, so across a row. This is mostly due to the charge increasing, so they'll get more polar as we go across a period. The acidity increases because the bond becomes more polarized as we go across. So since going across a period we hit more and more electronegative atoms, they are more able to attract the electron away from the hydrogen, and so our bond gets more polar. So these are our two trends for our acid. Now bases, on the other hand, are going to do the opposite. Base strength decreases across a row and decreases down a group. So it's the exact opposite trend to the acids. On a special note, the electronegativity difference between carbon and hydrogen is so small that CH bonds are nonpolar, so compounds like CH4 are neutral. They're neither acidic nor basic. Here's a chart to summarize those trends. The red arrows show the acid trends, the blue arrows show the base trends, and there are a couple of examples given for your comparison. Now, when it comes to the polyprotic acids, these were acids that had more than one acidic proton, so typically more than one hydrogen atom in them. These are going to have more than one acid dissociation constant. So there'll be an acid dissociation constant for the first dissociation. So how many, what percentage, what ratio of single hydrogen atoms dissociate, and then a second or sometimes even third dissociation constant for the next dissociation. If the difference between these is 10 to the third or more, it means the pH generally will depend only on the first dissociation. If there's 1,000-fold difference or bigger, it means that the first hydrogen is breaking off, and then the second one doesn't really do enough to matter. So that means you can just take the first one into effect for pH calculations. If it's smaller, that means we need to do two sets of calculations. We need to see what concentration of hydrogen is coming from the first dissociation and what concentration is coming from the second dissociation, since a different ratio will dissociate in each case. So let's take an example. Sulfuric acid is a polyprotic acid. Its formula is H2SO4, so it has two potential dissociations. The first dissociation has a very large dissociation constant. It's very strong, and a lot of the hydrogen will dissociate. The second dissociation is weaker, 1.2 times 10 to the negative 2. So, if we wanted to consider both dissociations, we'd make an ICE table for the second dissociation, taking into consideration that the initial hydrogen ion concentration is equal to the initial acid concentration. If we're told that we have a large dissociation constant, it means we're assuming that for every mole of acid we dissolve, we get 1 mole of hydrogen dissociated. If it's very large, we're going to assume it pretty much 100% dissociates. Then, just like before, we can determine X and solve for the final concentration of hydrogen. So let's walk through these steps in an example. We would like to know the pH of a solution that is 0.01 molar sulfuric acid. So to get the pH, we need to have our concentration of hydrogen ions. So let's fill in our table for what we know. Now, since we know the first dissociation is strong, we are going to assume that the first hydrogen comes off of every sulfuric acid molecule in solution. Therefore, if we add 0.01 moles per liter, and the first hydrogen comes off of every one, then we also have 0.01 moles per liter of hydrogen ions from that first dissociation. I've included here the two steps for the dissociation. So you can see in the first step, we dissociate one hydrogen and are left with HSO4. In the second step, we'll dissociate that second hydrogen to be left with SO4. So it's this second equation that we're making an ICE table for. We know about how this one's going to go, right? We put in 0.01 moles of this. It has a large K, so it completely dissociates. We get 0.01 moles here, 0.01 moles here. This one is the one that needs our calculation. So our reactant, we're starting with HSO4 and 0.01 moles of it, because we had equal amounts here that had to be created when they split apart. And we're starting with 0.01 moles of hydrogen ions, one of our products. We start with 0 SO4 because we need this to dissociate first. And then just like before, we'll fill in our unknown to be x. We're not sure how much of this is dissociating. We're not sure how much it's going to change by, but we'll just assume it goes down by some amount x. And likewise, then these each have to go up by that same amount. If one of these breaks up, or if x number break up, x number have to be created. And so then we write our equilibrium expressions. Now what we can do here is try to make this assumption that x is going to be very, very small compared to 0.01. If we do that, it'll save us from having to do a quadratic equation. So we can make that assumption initially. So we try that. We plug in our Ka. It's 1.2 times 10 to the negative third. The expression is concentration of products over concentration of reactant. And we make these assumptions in two places here. So we have x, our concentration of SO4, times 0.01 plus x, our concentration of hydrogen ion, divided by the 0.01 that we assumed was sufficient for the concentration of HSO4. And now we could also try to assume, again, if we assumed here that x was small compared to 0.01, we can assume the same thing here, that x is small compared to 0.01, that adding it to 0.01 won't make any real difference in rounding. If we do that, we just end with 0.01x divided by 0.01, which would get us x equal to k. So it's pretty clear that this assumption was no good. We cannot assume that x is small, because if it is, then these numbers cancel out to 1 and our x is equaling our dissociation constant, and that is not practical. So back to work we go. We don't make any assumptions here. We take our same starting equation, but plug in the full expressions for the hydrogen concentration and the HSO4 concentration. Now from here, you do have to simplify, get a quadratic equation, and solve, but we get a much more reasonable value for x, 0.0043. This was not less than 5% of our initial value. That's why our assumption did not work. All right, we've got an x value. We plug that into our ICE table, meaning we're finally able to find our equilibrium concentrations of everything. The equilibrium concentration we cared about was that of the hydrogen ion, because this is what we're going to use in our pH formula to calculate our pH of 1.8. We have a low value of pH, very acidic. That's what we are expecting. Here's a table for reference of some of the common polyprotic acids. You can see we can have, in most cases, 2, in some cases 3 hydrogens available. Typically, it's the hydrogens attached to oxygen that are going to be dissociating. And so we've reported the first two or three dissociation constants for each of these. And so you can see in many cases there is a large difference between the first and the second. 10 to the negative 5th versus 10 to the negative 12th. Now in a case like that, there's a large difference. We would only need to look at the first dissociation for the pH. These ones over here get so small in some of these cases that they're not significant. However, in other cases where they're very close, like citric acid here, they're only separated by a factor of 10 here, a factor of 100 here. These are all going to be significant. There's not one that's so much larger than the rest that it takes control. All right, a quick final couple of notes on some more specific types of acids and definitions to finish up the first part of this unit. So we've got a couple specific types of acids that are important. There are oxyacids, in which a hydroxide ion is bonded to another atom. Let's just say this general atom is Y. The more electronegative this Y atom is, the more acidic the acid will be. So if you've got an oxyacid where you've got an O bonded to an H somewhere, the more electronegative your additional ion is, be it chlorine, bromine, or iodine, the more acidic your acid's going to be. If you have a series of oxyacids, see these all have OH bonded to chlorine. Acidity increases with the total number of oxygen atoms. So we've got 1, 2, 3, 4 oxygens. We get more strongly acidic as we add oxygen. Carboxylic acids occur when there's resonance in the conjugate bases, and this stabilizes the base and makes the conjugate acid more acidic. So for example, these are two resonance structures of this acid, and the fact that there are resonance structures in this compound means that the conjugate base is more stable, and as a result, the conjugate acid is more acidic. The strength of this type of acid will increase as the number of electronegative atoms in the acid increases. So these can become very large, long chains, and as we add additional electronegative atoms, the strength of the acid increases. Alright, which brings us to our last definition here. One more definition of acids and bases to add to our knowledge. We had two so far. We talked about the Arrhenius definition of an acid and a base, which said that acids create hydrogen ions, bases create hydroxide. We talked about the Bronsted-Lowry definition, which said that an acid was a proton donor and a base was a proton acceptor. So this was more useful, or I guess more general to us than the Arrhenius one, because it focused on the electrons in the compound itself, rather than the substances that are created in water as a result. So a Bronsted-Lowry acid could be considered to be an electron pair acceptor. The Bronsted-Lowry acid typically, by that definition, is considered a proton donor, but we could look at it from sort of the other angle and say that instead of donating a proton, it's accepting an electron pair. And this would give us the Lewis acid definition, which just gets, again, a bit more general. A Lewis acid accepts an electron pair. A Lewis base donates an electron pair. Lewis acids and bases are more general because they don't need to contain protons. The Bronsted-Lowry definition was dependent upon proton transfer. The Lewis definition depends upon electrons, and everything has electrons. So it's our most general definition possible, and we're going to look at a picture to see this definition explained. So a Lewis acid generally has an incomplete octet somewhere. So BF3, if you remember when we drew those Lewis structures, the boron had an incomplete octet. It had 6 valence electrons on it. that would be a Lewis acid. Transition metal ions are also typically Lewis acids. To be a Lewis acid, the substance must have a vacant orbital into which it can put the electron pairs. So we said a Lewis acid accepts electron pairs. It has to have a place to put them in order to accept them. And so finally, compounds with pi bonds can act as Lewis acids as well. Here's an example. CO2 gas being dissolved in water to create H2CO3. I think I've got this, I've got a different one on here to demonstrate this. So this equation, this reaction, has been drawn out with the Lewis structures to make this definition a bit more illustrated. So our acids are the electron pair acceptors. So we can see that when this reaction takes place, this electron pair on nitrogen moves to the boron or gets shared with the boron. In either case, the boron was the one here that was accepting extra electrons. The nitrogen, before and after, doesn't have any more or less electrons. It's the boron that changed. The boron accepted some. It had its incomplete octet, and it accepted that electron pair. The nitrogen is the one donating or sharing its electron pair. So we can see why this definition allows us to include more into our acid definition, because we didn't have any movement of hydrogen here, so we wouldn't have fit the Bronsted-Lowry definition. We didn't create any hydrogen in water, so we wouldn't have fit the Arrhenius definition. But when these two combined, we could look at it as an acid-base reaction based on the Lewis definition. Electrons were donated and accepted. The base, again, was the donor here. So anything that could be a Bronsted-Lowry base is a Lewis base, but the Lewis definitions can include other things as well. We could also look at complex ions, which are transition metal ions with an attached ligand. And a ligand is a Lewis base with a lone pair of electrons. That's its definition. So a Lewis base is a substance that has an unshared pair of electrons in its structure. So if we've got a transition metal with an attached, something we can identify as a Lewis base because it has an unshared pair of electrons, we have what's called a complex ion. Here are a couple of examples of common Lewis bases, and we can visualize if we drew out the Lewis structure here, we'd have two non-bonding pairs on oxygen. Here we'd have a non-bonding pair on nitrogen. In all these cases, there's at least one unshared pair of electrons. So if any of these get attached to a transition metal ion, we build a complex ion. So we've got our acid definition. It accepts an electron pair. Our base definition, it donates an electron pair. And then the number of ligands attached to a central metal ion is the coordination number of the metal. Typically, this is 2 times the charge of the ion. Okay? So the number of Lewis acids we could attach to a central ion is given by the coordination number of the metal, which is typically 2 times the charge of that metal. The transition elements are able to use the d shell valence orbitals. So when they've completely filled these d orbitals, they form white compounds and give us colorless solutions. This is what was happening, by the way, in our iodine clock reaction. We were forming complex ions, and when they formed, they filled all these sublevels and made the solution colorless. a different complex ion contributed to the blue color. So that's why if you were watching at the end, we were able to take it back and forth a couple times between clear, colorless, and blue, depending on which complex we were allowing to form. The greater equilibrium constant of the formation of the complex, the more stable the complex is. So if we've got an equilibrium constant for the reaction that forms a complex, the greater it is, the more stable our complex. Don't worry too much about these final points here, these additional notes. They're useful, but they are a bit specific and niche. But hopefully that was a decent introduction into them in case you run into them later.